In the previous section, there were several assumptions that came up in arriving at formulas for computing the endpoints of a confidence interval. Two key assumptions are that the population should be normally distributed and that the sample be one of many possible samples that could have been drawn from that population. These assumptions are conditions that affect the validity of any resulting confidence intervals. Starting with the first of these assumptions, the population does not actually have to be exactly normally distributed, and in fact, if the sample size is big enough, the confidence intervals considered here will be accurate for almost any population. This is true in part because these confidence intervals are based on sampling distributions rather than population distributions, and if the sample size is big enough, sampling distributions tend to have the expected shapes even if the population is not normally distributed. For example, consider a population distribution like this one, which is not a normal distribution, and a sampling distribution of the sample mean based on samples drawn from that population. This plot shows sample size n equals 2. With such a small sample size, the sampling distribution is skewed to the left and is not a normal distribution or any other common distribution. If the sample is larger, however, the sampling distribution can get very close to a normal distribution. With sample size n equals 30, for example, the sampling distribution is almost indistinguishable from a normal distribution, which is the expected distribution in this example. A common guideline is to use a sample size of at least 30 if the population distribution is not close to a normal distribution. Smaller samples are fine if the population is approximately normally distributed, and otherwise the sample size should be at least 30. Even when the shape of the population distribution is unknown, it's usually possible to get some idea of that shape by considering the origin of the data. As an example of how that can be done, consider planting seeds in a garden where conditions are such that only some small fraction of the seeds germinate and grow to become mature plants. It's reasonable to expect that the distribution of plant sizes, including the seeds that did not germinate, probably looks something like this. So even without knowing the exact shape of the population distribution, it would be appropriate in this example to collect a larger sample, since this distribution is not similar to a normal distribution. The mature plants, on the other hand, may all have roughly the same size with relatively small variation between plants, so it's reasonable to expect that the distribution of mature plant sizes probably looks something like this. Since this distribution is close to a normal distribution, it is reasonable, again without knowing the exact shape of the distribution, to expect good confidence intervals even using relatively small sample sizes. The second general assumption is that the sample used to compute the confidence interval should be one of many possible independent random samples that could have been drawn from the population. Among other things, this requires that the sample be representative of the population. For example, considering again a population of plants in a garden, this shows a population where the plants near the right side of the garden are small relative to the other plants. A sample drawn from the right side of this garden would not be representative of the population and so would not lead to a good confidence interval. A sample drawn selectively from some part of a population is called a biased sample. One requirement here is that the sample not be biased. Also, the population needs to be big enough so that it is possible to draw lots of independent random samples from the population. If the population is the same size as the sample, for example, then every sample will consist of the same individuals as every other sample, so every sample will give the same statistics and there would be no real sampling distribution. A common guideline for satisfying this condition is that the population should be at least 10 times bigger than the sample size so that it is possible to draw lots of samples without having too many of the same individuals in every sample. To summarize, the conditions for the confidence interval formulas from the previous section and in the next few sections are that the population distribution should either be close to a normal distribution or that the sample size be at least 30, that the sample be unbiased, and that the population be at least 10 times bigger than the sample.